Okay, folks, today we're going to start our discussion of global climate and what controls global climate. So we can see in this animation that's going on here that we can see temperature changing on average over the entire Earth over the course of the year. And as we're watching the colors, I want to direct you to down here just to take a look at what the color scheme is. So those warm colors are going to be warmer temperatures, and the colder colors are going to be colder temperatures, as you might just guess by looking at something like this. But look up in the corner and you can see what month is reflected by each of these global averages. And one of the first things that stands out is that there's this sort of breathing motion that goes on almost, where as it gets cold in the northern hemisphere during the winter, it simultaneously gets a little warmer in the southern hemisphere. And then the reverse happens as we switch to northern hemisphere summer. We can also tell that near the equator, it's much hotter on average than it is closer to the poles, and that in between in the temperate zones, you get a strong seasonality effect where during the summer it's warm and during the winter it's cold. And we can see that that varies over the whole planet in different places and affected by different things like what's going on over here. But we'll talk about what is controlling the climate in general, what's controlling its seasonality. We'll add into this a discussion of precipitation, and then later we'll extend it to current changes that are going on today in a future lecture. Before we begin, I do want to note that climate is a belief-charged subject, that there are a lot of personal opinions that go along with studying climate. Today, we're going to have a little bit less of that because we're just covering the basics of climate. So we're going to be looking at things like, temperature and precipitation and seasonality. Things that anybody can agree that we have a climate on Earth's surface, and we want to talk a little bit about why we have the climate that we do. In a later lecture, then we'll talk about anthropogenic climate change. I want to note that I don't require that you believe either of these topics that I'm going to cover, but I do expect you to know what science, quote unquote, believes, and I want you to be able to answer questions based on what science, quote unquote, believes, with the perspective that if you want to be able to disagree with a particular topic, you should still understand that topic to know exactly what it is that you disagree with. So we'll break this up into 3 sub-lectures. First, we'll talk about the sun and climate. Then we will change and look at Earth's current climates, and then we will end with the discussion of the greenhouse effect in general. First thing I want you to think about is, what do you think the primary control on Earth's climate is? Why do we have the climate that we do? And you might start by thinking about what are the differences that seem to cause seasons, because that can help you think about when it's warm, what are the conditions like? When it's cold, what are the conditions like? And what do you think it is that's controlling most of those changes? In general, the largest effect on Earth's climate is the sun. And that's pretty understandable that, when we have long hours of sunlight in the summertime is when we're going to have the warmest temperatures. And then in the wintertime, the sun is not up for nearly as long. And the sun is never quite directly overhead. Because of that, the warmth that we're getting from the sun is reduced in the wintertime. And that is really the big driver of changes in seasons, exactly what our relationship is to solar energy coming in. And we'll talk about that more in a little detail later. I'll note that Earth's average surface temperature today is about 15 Celsius or 59 Fahrenheit, right? Cooler than room temperature, but say a nice spring day for us, perhaps. Without the sun's presence at all, right? If it were eternally night everywhere on Earth, Earth's surface temperature would be a whole heck of a lot colder than that. It would be about minus 250 Fahrenheit or minus 157 Celsius. So clearly the sun is having a very large impact because the majority of the temperature on Earth's surface is controlled by the sun. Now, I want to note that that doesn't necessarily mean that all changes in climate are due to changes in the sun, or that the sun is the only factor controlling climate. Other factors matter too, as we will discuss. But I do want to note that the primary control on Earth's climate is, in fact, the sun and solar radiation. When I say climate, what do I mean? I mean the predominant weather patterns over a period of many years at a particular location. And we can break that down essentially into three things, and we can add more detail to this if we'd like, but we want to think about the temperature as part of climate, the precipitation as part of climate, and then the seasonality, the yearly pattern in when we get temperature and precipitation changes. And if we categorize it in a relatively simple way, we can break up Earth's climate into polar and subpolar, or temperate, or subtropical, or tropical. So that's sort of the coarsest level of detail we can go into, which is really varying mostly based on the temperature. So in the tropics near the equator, so when you have tropical climates. And then slightly north of that, you have subtropical climates on and on into temperate, and eventually polar and subpolar climates closest to either pole. We could break that down into even more detail if we wanted. We can break up, instead of into 4 categories, we can break it up into 14 or 15 categories or even more if we really want, where we're bringing in the effects, especially of precipitation and of patterns over seasons. Or we could even break it down individually and look at each month and consider in very fine detail how the average temperature and precipitation changes in a particular location over a year. So here our bars are average precipitation, and then we've got an average and a daily maximum and minimum temperature as well. And so you can see in Knoxville, it's going to be warmest June, July, and August. We get the least precipitation in late summer, early fall. And we can have a very quantitative understanding of climate if we want to as well. So these are all levels at which we can talk about climate, either coarse or fine detail. How does the sun actually control Earth's climate? We've mentioned that it does, and now we've mentioned what climate is, but how is the sun actually controlling Earth's climate? Well, the basics of it is that we want to think of the Earth as a system, and that at what we call steady state, the energy going into that system has to equal the energy going out. And by balancing the energy going in and coming out, we get a particular temperature at each point on Earth, or Earth in general, if we want to take a global average. And the big input of energy into Earth is what's coming from the sun. And that's why we say that the sun is the primary control on Earth's climate, because solar radiation originating from the sun comes down, and some of it bounces off of, say, the clouds or of Earth's surface, and that doesn't do anything to warm us up if it bounces off and reflects directly to space. But plenty of that solar radiation is absorbed by water vapor, by dust, by ozone, by the ground itself. And when energy is absorbed by something, its temperature is going to increase. As the temperature of Earth increases, it actually emits radiation. So if you ever put your hand, over, say, the warm asphalt in the summertime, and you can feel heat coming off of that, what you're actually feeling is infrared radiation. The Earth is actually emitting radiation. And if left unimpeded, that radiation can go all the way to space. So there's a balance between the energy coming in, absorbed by Earth, and the energy going out, emitted by Earth because it has a particular temperature. When Earth's temperature increases, it emits more radiation. And so that sort of acts as a cooling mechanism. But the balance between what comes in and what goes out is what is going to control Earth's overall temperature, and is what's going to control Earth's temperature at particular locations too. Where does solar energy actually come from? What's the process? Why does the sun release so much radiation? It's a process called nuclear fusion. So certain isotopes in the sun, mostly of hydrogen, but also other things going on in here that we're not showing, we can actually combine these nuclei into entirely new elements in a process called nuclear fusion. For light elements like hydrogen and helium, doing that takes a lot of energy to get it started, but then it releases tremendous amounts of energy. And that's a process that we call nuclear fusion, because we're fusing two nuclei together. It releases a lot of energy. That energy heats up the sun, the material around it, overall 600,000 kilometers of depth, give or take, that the sun is. All that matter. Most of the solar system's matter, in fact. That energy eventually reaches the sun's surface by bouncing around in between different molecules in different forms. But then a lot of that energy can be released from the sun as light or other electromagnetic radiation, as heat, or as currents of matter. So, like you can see the solar flare shooting off here. Now, oftentimes those the currents of matter are not what is reaching Earth. Most of what is reaching Earth is radiation. So visible light, infrared light, ultraviolet light, things like that. And as it reaches Earth, it can be absorbed by different parts of Earth, its atmosphere or its surface, and Earth's surface warms up. Parts of Earth's surface, especially depending on what their chemical makeup and what color they are, is a good reflection of how much those surfaces can reflect sunlight. So bright things reflect a lot more sunlight than dark things do. In response to warming up, Earth or any other object will emit heat, and as a result, it will cool down. And so once again, the balance of Earth's climate is controlled by incoming solar radiation on one side and outgoing radiation on another side. And depending on how you want to account for things, you could very carefully control and count the stuff that's being reflected, or you could just worry about the stuff that actually makes it into Earth's atmosphere. At any rate, we're balancing incoming and outgoing solar radiation to control Earth's climate. There are very small inputs from things like geothermal energy, right? We know that Earth's interior is warm, and so it's emitting some heat over time naturally. But in the grand scale of things, it's actually a very small amount of heat compared to what's coming from the sun, and then ultimately what's leaving Earth's surface. So what are some consequences of the fact that the sun and its radiation is what's controlling climate on Earth and on other planets? Well, one thing is that planets closer to the sun are generally warmer. So if we look at that, we can see temperature from the sunlight, excluding reflected light, is in this row here. So this Mercury is closer to the sun than Venus, than Earth, and ultimately than Mars is the furthest rocky planet from the sun. And so if we just look at the temperature of the planets that are closer tend to be warmer. There's a little bit of a hiccup because we would expect Venus's temperature to be slightly lower than Earth. Just because Venus is so much brighter, it actually scatters more light. So that's the only reason that Venus's expected sunlight-based temperature is lower than Earth. But in general, as you go closer to the sun, you get to those higher temperatures. And then further away, you get lower and lower temperatures. I'll note for now that we see that our actual measured temperatures at some of these locations are close to those. So on Mercury and Mars, those are very similar. The true temperatures are similar to what we would expect just accounting from the radiation coming from the sun. And in other places, they differ. So here they're differing by about 33 Celsius. And on Venus, they differ by a tremendous amount. And we'll talk about why that is a little bit later. Now, why are the planets closer to the sun so much warmer? It's because the sunlight spreads out over a wider area when the planet is farther away. Or conversely, planets that are closer to the sun have more concentrated sunlight. So because that energy is spreading out over a wider area when it hits Mars, it's not going to warm up the surface nearly as much because you're not getting as much sunlight over a given area as you do at Earth. And Earth doesn't get nearly as much sunlight over a given area that Mercury does. It's about the concentration of solar energy as it spreads out, leaving the sun. Astronomers have considered this in the context of what we call the habitable zone. And NASA and other space agencies are doing a lot of exploration recently, trying to identify and locate planets outside the solar system. We're just developing over maybe the past 20 years or so technology that is really enabling us to just find how many planets are out there. And we're doing that a lot. We're thinking about, well, where might there be planets like Earth outside our solar system? And we've reduced that to the concept of the habitable zone, which is the region around a star that is the correct temperature for liquid water to exist at least over some of its surface. So why is liquid water being present so important for habitability? Well, all of the life at Earth's surface seems to require liquid water. Liquid water is really good at enabling solutes within cells to move around, for example, because you can bounce, materials, nutrients that organisms need through a cell only because the liquid allows material to move through them. So while it's possible that we might find some exotic life out there that is not dependent on liquid water existing, it is a really good starting point. And so we can define the habitable zone around stars by how much sunlight it's getting, essentially. And we can look and map where some of the planets that are much farther from Earth, that aren't around our sun, but around other stars, based on the temperature of their star and exactly how much solar energy they're getting.